Hey, welcome everyone to the last session of the day. So this session is actually starting with a bit of data engineering, and then I want to talk about how we can use generative AI for data platforms. And then I want to talk, that's the thing we have to talk, and then I want to turn it around and talk about why do we need data platforms for generative AI. So it's almost the mirror at the end, right? So I'm Frank, I'm based in Munich, Germany, and it's the second time I'm here. I was giving a talk last year at Devoxx in Athens. I liked it so much, I reapplied and I got accepted again. You're not here for me, you're here for the content. So I'm working for a company with the name Databricks, and it's a quite unusual company. It was started by 7 different people, all coming from Berkeley and Stanford, so highly academic, and now we're like 6,000. So sometimes I get an email and someone says, hey Frank, can you connect me to someone who's doing Scala or Python or Java at Databricks? And like, no, I can't. There's just so many people. I wish I could, but I can't. We're actually hiring, so before you write to me, just look at the online jobs. And the other cool thing I think about Databricks is it was founded by the original creators of like 3 super cool open source projects. And probably the most popular one is Apache Spark. Spark has 1 billion, not a million, but 1 billion downloads per year now. And this data is almost a year old, so it might be much more today. Actually counting the pip installs and the mavens and whatever. The second one is maybe one of the most dominant MLOps frameworks, MLflow. And then you know all these discussions about data formats for the lakehouse architecture. Delta Lake is the third one. There's many, many more. There is like Delta sharing. There's a couple of others. And very often people say, hey, is it all open source? No, some things are product. But then the Databricks typical thing is not asking, does it get open sourced? It's more or less like, when does it get open sourced? However, and that's also what I'm trying to explain, typically, our main goal is not pushing out open source. No, our main goal is to solve like super tough data and AI problems. And actually AI problems even before AI was popular as it is today. So we have 10,000 customers. We have quite a bit of venture capital from all the 3 big cloud providers. And we have a unified, multi-cloud, simple platform for data engineering, data, and AI. And that's what I want to talk about. First thing I want to briefly mention is streaming data. And streaming data is, if you look at, does it move? Yeah, cool. It's an animated GIF, so it should move. Streaming data is the cool thing. So when I left to come here like 2 days ago, I was calling a taxi in Munich, Germany, and it was half rain, half snow 2 days ago. Remember, imagine this, no, half rain, half snow. So I called the taxi, used the phone, and someone responds and says, which floor do you live in? And I'm like, I come to the street, don't worry. And he says like, it will be there in like 15 minutes. And I'm like, okay, I'm not coming to the street. Can you tell the driver to ring my doorbell because of the, snow and rain? Now, this is what we want to have. Now, we want to have this small moving dot, and this is what I get here in Athens if I ask for an Uber to come to Megaron Musiki. No, it works really well, and we are used to that, and we want to have this. And the cool thing is these tiny dots, they're like small data. It's not the big data thing that we often do at Databricks. It's small size data. No, it's continuously produced. It often comes with this expectation that it's processed in time. You wouldn't like this display if it's not moving, if it's not accurate, if it's not processed in time. And for us, very often, like the way we see this is not the super, super low latency. It's more the throughput thing, but with a low latency. And then it's more the write time versus real time. This is what you see here on this slide. So very often the streaming paradigm is more the way you program it. And once it's programmed, you have a setting. It's not this real, it's not this Mickey Mouse slider, but it's a setting where you say, look, I want to run this pipeline continuously, or I want to trigger it like more or less the old batch way every Friday afternoon at 2 o'clock. And you can define this, and you can have some workflow system that lets you schedule this like once an hour, once every 5 minutes. So there is this virtual slider that you have once you do the right programming. Having said this, I want to also briefly talk about latency and throughput. What's the difference between latency and throughput? One of them is easy and the other one is hard. So the easy one is throughput. Throughput is easy until it's not, no? So if you need more throughput for your internet line at home, you just ask your telco provider and they give you more, you pay more, you get more throughput. If you need even more, they say, well, then you need cable or fiber and you still get more. If you still need more, then you get to some border and they say, okay, if you have the money, we come and we dig open the street in front of your house and we put more fiber and whatever, and then you could still get more. But this is the part where it's not that easy anymore. The same is true if you think about data engineering, with Spark. You could just add one more instance to your cluster now, and you get more throughput. And at some time, people say, look, but what if we need more throughput per instance? You know what I mean? And then it gets hard again, you know. So to a certain degree, throughput, you just throw more money, more resources at it, and you solve the problem. But then there is this limit. Now, one idea of this lakehouse concept is that you have your data in the data lake, and then you have this thin open source layer, Delta.io, that does the table format that gives you ACID transactions and a rollback and versioning and deep and shallow clones and all these things that you expect from a data warehouse. And the side that we come from, the data engineering side, everyone understands, look, it's basically the company was founded by the guy who originally created Apache Spark. So this is what we do really well. And then for a while, we had this discussion about, yeah, but how well does this work the same data set as a data warehouse? Because that's the promise of the Lakehouse. And of course, honestly, it took us some time. And it got better from version to version. But then there was this limit, you know, like when the telco provider tells you, we can do more, but then we need to dig open the street in front of your house. So what we did is we re-implemented the Spark API in C++ and made it more performant, obviously, and more suitable for modern architectures and for vector processors. And this was this jump of 2.2 in throughput. So it was mostly a throughput thing and making it more suitable for data warehousing with big data. Did it work? Well, it worked kind of. Yeah, it actually worked pretty well. That's an understatement. So we won the new record for TPCDS, which is an official benchmark, and it's also officially run by the Barcelona Supercomputing Center. And we beat the old record by a factor of 2.2, which is quite a lot. If you're twice as fast as the previous one, and you can imagine the previous one was already pretty optimized, that's not bad. And that's kind of, I mean, if you look at this, maybe this is more visually convincing, but winning this benchmark, I think, was the final breakthrough in businesses accepting that we are really up to compete with, you know, the Redshifts and BigQueries out there. But we have this single platform that brings a lot of benefits. Okay, now I talked about the easy part. How about the hard part about latency? I spent a lot of time in, years ago, 15, 20 years ago in high performance computing, and they had this joke like, do you know what to do to speed up something on one of these supercomputers by a factor of 2? Do you know? Anyone knows that joke? It's a running joke. The answer is, take 18 months off and go surfing. And the idea is, you know, we had this Moore's law, everything doubles in 18 months or 2 years. You get twice the compute power, you come back, you run the same application, it's twice as fast. Sounds like a free lunch. The only problem is it never worked, because when you came back from surfing, you still had your old supercomputer and it was still having the old processors, so that was more a joke. Well, kind of joke, but if you think about this today, and you have your application in the cloud, and you run the same application on the newest EC2 instances that are available after 18 months, they might be slightly cheaper and much faster. So maybe now you have this free lunch. And talking about Munich, where I live, this is actually the place where people in Munich surf. Munich is like 800 kilometers away from the sea. There is a river in the middle of the city. And you see, this is the left side and the right side where the people are standing. And there's a steady wave behind the bridge. So people even from Australia come to Munich, bring their surfboards to surf. Now, why am I telling this related to latency? I told you latency is hard. So if you want to improve the latency, that's super, super hard. Improving Spark latency. Honestly, the best recommendation I have for you is just take a year off and wait. And the answer is, there's a huge team that we support that is working on this project, Lightspeed. And I don't expect you to read all this. I'm happy to share the slides afterwards, and then you can click on the links. And they almost exclusively focus on latency now, because obviously that's the thing to decrease, and that's super important. So there's lots of, I don't want to say tiny breakthroughs, because otherwise if they see this video, they will kill me. Breakthroughs where they kind of improve latency by 10, 20, 40, 60%, depending on what you do. It's stateful, stateless pipeline. They work on everything, and it's amazing. So it's really just wait, and it gets better. And if you have a kind of application, well, try and rerun it with the newest runtime, and then it will perform better. This is one of the blog postings they published. So the Spark latency for unstructured pipelines is going to sub-milliseconds now. And that's really on par with Flink, and we're just working on some other paper where we even show if you have these, sorry, I forgot the name, from the EC2 instances that go away. What's the name? The spot instances. So if you have spot instances that you use for your Spark cluster and they break away, Spark is even faster in recovering and giving you a lower latency and better throughput. All right, and then the last part I wanted quickly to emphasize is that the whole Lakehouse platform is going towards serverless now. Remember, it's multi-cloud anyway, so it's not really based directly, or not that you would see, it's not based on AWS Lambda or something. But whatever I listed here, and when I wrote this list, like notebooks and pipelines and AI models and SQL, and that's actually much, much more like a vector database and all the stuff that you need for Gen AI. This is all completely either serverless now or getting serverless as we speak and in preview right now. So the idea is you should focus on the function, what you really want to do, and you should stop configuring and optimizing clusters. And when I speak to engineering, they tell me that even now they see in the people who do the preview that if you give people obviously less opportunities to misconfigure a cluster, at the end it's much more reliable. So the whole serverless also has this touch of being more reliable. And as I mentioned, this will work on any cloud then at the end. Okay, so this is the hard part where I feel like I don't even want to be here. I brought you a super cool application, and now we have an internal glitch that prevents, since yesterday, that prevents me running this application and having fun with you guys. What I wanted to do, or what I built, what is not working right now, is a serverless application that uses a serverless single-page web application that is hosted on S3. So it's an HTML file with a little bit of Bootstrap CSS, which is writing live events coming from phones, like from the motion detector in your phone, into an AWS Kinesis stream, which is then picked up by the Databricks ETL, which is called Delta Live Tables, where you can do streaming and non-streaming ETL. And then I have a second pipeline in a Spark notebook that is reading from that first pipeline and displaying those events in real time. And I thought we could do this together here, so I was hoping for hundreds of people, and now we have this glitch that I don't even want to think about. So I still want to show you the code, because I mean, come on, it's Devoxx, and I want to show you how this looks like. It actually looks like this. First of all, if you code these pipelines, they could be in SQL or Python. The idea is that we want to give you a way to declare what you want to do. So it's a little bit like this Kubernetes principle where you say scale to 10, but you don't tell people like how many items they need to add or remove. This one I wrote in Python for two reasons. One, because I could and I wanted. And the second reason, when I wrote this, for ingesting data from Kinesis, we still had to code this in Python. So typically we tell people, choose whatever you want, SQL or Python. But at the time when I built this demo, for the ingestion from Kafka, Kinesis, PubSub, Pulsar, you had to use Python. And if I show you the code, you also understand why. The interesting thing is this limitation has gone away now. So if you today program the same thing, you could code this in SQL, and in SQL we have a method that says read Kinesis, read Kafka, read whatever. Now, if you look at this code, it pretty much looks like if you've ever seen Spark streaming code, this Spark read stream, format Kinesis, then you give it the name of the stream, the region, the keys it needs to use to connect to that stream. That's actually standard Spark structured streaming code. And then the fun part where we declare the pipeline, the first element of the pipeline, which is a streaming table, it's this Python decorator. So it's, zoom in a little bit, it's this DLT table, and you can comment it. The table name is the name of this function, unless you define it otherwise, and it returns the stream that is defined here. And now this builds on each other, like the second table is building on the first one. If you write this in SQL, it's one of these CTAS, create table S, select from the previous table. Now here it's like a line, like a linear relationship, but obviously in a complex ETL scenario, this could be a huge mesh. So the next one is a view. View means it's not persisted, it's not backed up by Delta IO. It's just a view. And yeah, because I don't want to persist it. And I'm reading that raw stream that I defined in the first one. Where was it? This is the raw stream table. And I'm reading it here. I select the partition key, and then I need to do this mapping from the schema because, you know, the Kinesis thing is more a blob, and I need to map this to schema. And finally, I have a gold table, which is the sensor table. And I say gold because we think about this we call it medallion architecture, which we probably stole from the Greek people with the medallions that you get at the Olympics, bronze, silver, and gold. And the idea is for bronze, you do the raw ingestion without any transformations that could go wrong. For silver, you do the cleaning and some aggregations. And the gold tables at the end, they're the tables you expose downstreams for AI, for BI dashboards, for reporting, for whatever. It's just an architectural idea. Sometimes people say, well, I don't have silver. It doesn't really matter. We don't force you to do that. It's more like a convention, like a naming convention. Anyway, that's the last one, and that's the one you could use downstreams. And let me see, I have another browser here where I did another example. And like 2 years ago, I had an example where I was ingesting data from Twitter, and I had a small job using the Twitter API and writing that data, data lake style into an S3 bucket. And then we have something which is called autoloader, which is basically watching that S3 bucket and ingesting the data in an incremental way. That's the cool thing about streaming. So it will only ingest one file once, and that's autoloader. And then I was using this bronze-silver analogy again and running some Hugging Face transformer for sentiment analysis for these tweets. And I'm showing you this because I wanted to show you the SQL version, and it looks like this. So we ingest with a streaming table. It's just create streaming table. I even name it bronze to make it easier for you. And then remember I told you it's CTAS, create, table, S, select everything. Cloud files is the synonym, the tech word for this autoloader. And then we have the whole data stored in a volume. In a minute, I will show you some architecture of the lakehouse, and you will see that the core piece, and maybe the most important part of the whole lakehouse, is a centralized layer for governance. So one cool thing about the lakehouse is we can govern with, allow and deny and lineage and tracking and all this SQL tables and schemas and views the same way as volumes and files. And that's like this whole unified governance. Now this is creating the bronze table. Let's just look at the next one. There's a silver table, and guess what? The silver table is create. Well, it's a materialized view. I'll tell you in a minute what that is. So it's create the view, the silver view, and then as select a number of columns from the bronze table. If you ingest from Twitter, you get like 40 different columns. They all have a type, and you need to know the column name and the type. And all this is done automatically here, like the type inference, the schema inference is done here automatically by autoloader. Now, when I showed this to a group of new people starting at Databricks, one of them was coming from AWS, and he was like, okay, Frank, but you don't tell people the hard thing you need to do, like, setting up an SNS queue and setting up, the SQS queue and the SNS notification to make this work in the background. Well, it's all done by the system, and you don't have to do this manually. That's the cool thing. And again, it's not only working on AWS, it's also working on GCP and Azure. So it's this high level of abstraction that we think is the right way to do data engineering these days. And that's actually most I wanted to show you here in this demo. If I click on catalog, you see basically the, let me see, I think this was under Frank. And then I had the motion demo. Here it is. You see the tables that are created. And you also see for the first time this interface to governance. So under one naming schema, which is for us the first one, the first name is the catalog, and the second one we call schema or sometimes database. So under one catalog and one schema, we can have tables and volumes and models and functions. And these are the tables created by the pipeline. And if I click on one table, I also see the lineage for that table. So if I click on lineage graph, you see the dependencies. And now this is all just built in. It's just working out of the box. And I'm always teasing a good friend of mine. He also lives in Munich, actually next door. They run their own data lake, and they built their own, they evaluated their own governance solution. And they spent like 2.5 years now integrating their governance solution into their lakehouse and into their data warehouse. And they're still implementing and integrating. And I always say, like, can I see just such a graph, where stuff is coming from? So we have no volume here for this one. But if data was ingested from the volume, you would see it here. If the gold table is used as a feature table for an AI model, you would also see it here. And that's a super cool thing. You get this end-to-end lineage, which helps you a lot if you think about responsible AI. So it's not just having one data lake and making it accessible to everyone, because otherwise your tools wouldn't work. You can have this fine-grained granularity and clearly define who's allowed to see what. And then you can also backtrack from your model and see what data was used to feed this model. And that's pretty amazing. And I think that's pretty unique from what I know, what the others do. All right, let's go back here to the slides. The demo I wanted to show you was using this single-page web application, Kinesis Stream, ETL, that's the Delta Live table thing I just showed you, and then another Spark streaming notebook for reading the data and displaying what happens over time. Like, the idea was, if a lot of people generate these events, I want to average them on on a 1 second window basis and show the average. And then I thought I build a workflows around that and even show you the SQL part. So I built all that. It's just not working that well, except like the code that I could show you. And then if you think about what of this is serverless, well, everything is serverless these days. That's the cool answer. So you can basically stop thinking about cluster and stop configuring them and stop tuning them. So that's the only architecture slide I promise you, but I have it twice in the same deck just for being able to explain things easier. Remember what I almost already explained to you. We start with a data lake. So it's a lake first approach. You leave your data in your data lake. If it's on the Google side, on the Azure side, on AWS side. So it stays in the data lake. There's this thin layer of Delta Lake, Delta.io. It's a Linux Foundation open source project that gives you the table format, like the transactions and the rollbacks and the shallow and deep clones, etc. Like all these goodies that you expect more from a data warehouse now. And then we had this huge discussion ongoing for many years. Is it Delta.io versus Hoodie versus Iceberg versus I don't know how many others there are out there. And last year we came up with Delta Uniform. So with Delta Uniform, you can have like one configuration. And then when we write out a Delta table, at the same time, we also write out Iceberg tables and Hoodie. So if you want to read this from, I don't know, from some web-based data warehouse that is using Iceberg, you can do it. If you want to read this from BigQuery, you can do it as well. So hopefully this table format discussion is mostly ended by this. And then there's Unity Catalog in the middle. I told you that's the core thing. Having this governance is really essential. And then later I want to talk about the intelligence engine. And what you've already seen is Delta Live Tables, the pipeline part. Workflows I'm not showing you here. The pipeline part, remember streaming tables, I told you they're good for ingestion. The cool thing is they ingest exactly once. They can ingest from Kafka, Kinesis, PubSub, any messaging system, but they can also ingest from an S3 bucket, and you can throw thousands or tens of thousands or millions of files into this bucket, and it will be ingested exactly once. And then we have materialized views. Like sometimes I say to my marketing colleagues, they're like pushing this a lot because it's new, and that makes sense. And then I tell them, look, but we had them like 20 years ago in the, those databases on premise with the red label. You know what I'm talking about. And if you look at what they are doing, it seems to be highly complicated to get them updated, to get them fresh. Like what we are doing, they're always fresh. If you do serverless, which is the new default now, they're computed incrementally. So in such a materialized view, you define a view, which is then pre-computed, and if the data changes, only the increments are computed again. So it's highly efficient, and it's obviously used to speed up dashboards and all the downstream things. We did another benchmark, and we won an ingestion benchmark. It was like ingesting 1 billion records for under $1. I linked to the blog post. It's actually a really, really good blog post to read. Some of the techies wrote it. And when I spoke to them, they told me, look, the cool thing is not really, the cool thing obviously for this blog post is the performance. But what they told me is, hey, in Delta Live Tables, we also have expectations. And I didn't show you this, but I should have. And these expectations, they guarantee the data quality. It's actually, the keyword is constraint. And we define like what should happen if the data does not match this constraint. And then we can log it, we can drop it, we can put it in a quarantine table. And they told me when they wrote this blog posting and they set up all our data for this benchmark, they discovered that the data in the benchmark was not correct. It was inconsistent. So many, many other companies submitted results for that benchmark, and us, because for the first time we used these constraints, we discovered that, hey, sorry, the whole benchmark data is not really correct. Right. I told you about workflows. In workflows, think about it as a serverless built-in equivalence or better solution for what you might do with Airflows. You pick any of these job types. It could be running a pipeline, it could be running a DBT task, it could be a Spark submit, any notebook. You define how it's executed, sequential or parallel, and then at the end you also define how you want it to be triggered. Now, triggering this could be by updating a Delta table, it could be by a file arriving, or it could be, think about workflows again, it could be started by a cron job by workflows. Okay, now what can we do with Gen AI in such a data platform? And I'll show you some slides quickly, and then I switch back and demo a few more things live, and that will be the end of the talk. Well, the cool thing is, once you have a single unified platform and you want to apply all this AI magic, you know where you get the data from, because the data is actually here in the middle in the Unity catalog, in the governance system. Now, if you have the data in the catalog, in one centralized place, and you know about all your tables, all your views, all your SQL statements, all your volumes, all your AI models, then you can do a lot of things, And all of a sudden, this whole generative AI makes a lot of things, makes a lot of sense. So we can use it to generate documentation. We can use it to explain code. Like the Databricks assistant is like an assistant that is built into the Lakehouse platform. This is also why we call it data intelligence platform. And then we have SQL. It's actually text to SQL for dashboards. I think this is a typo here. So you can type text and say, give me the top 10 the top 10 sensors that receive the most events, for example, and it would just create a chart for you. And the other project, it's too early to talk about it, is called Genie or Data Rooms, and this is where we have a natural language interface for your data sets. And this is like really, in my opinion, a whole level up from everything else I've ever seen that you could do by interacting with something like, GPT. If you set up such a data room with Genie, you could say, hey, for this public data set with the wind turbines, give me all the turbines that are not working correctly. And then the system would say, sorry, but I don't know what you mean with not working correctly. Can you specify? And then you say, yeah, not working correctly means they produce less than 80% of the output that the others produce on average. Now give me the number, and it would give you the number. So it's asking back if it doesn't know, and it's I would say one level up and more clever than what you would expect. So stay tuned until we can show this. And that's I'll show you a bit more here, but that's the using Gen AI to support data platforms part. And now, obviously, some of you know we've been in the news for two things. One is Databricks bought ML, which is the company that probably has trained the most LLMs themselves for business applications. And the other news, have you heard about DBRX? Anyone? I see a few hands. So DBRX is the LLM model that this team, which is now part of Databricks, has published. And I want to quickly tell you both. So the plan is, since we have this single platform for data engineering, and you need to do all this data engineering to have a good model, we want to support the whole spectrum. So everything from what every one of us is doing today, like prompt engineering, to everything we are doing also today. Who's doing RAG these days? Few people. So RAG, retrieval-augmented generation, means you have a vector database, you call out to this vector database, it contains the facts, you take these facts, add them to the prompt, and then send the new enriched prompt to your backend LLM. Why? Because then you can add the facts that you really want to have included in the solution. And then one step to the right, fine-tuning. This is when we give you a base model, and you say, look, actually, the real benefit of doing all this LLM stuff is not calling out to ChatGPT, which is fed by the whole content of the internet and whatever more. what you really want to have is your data in this model, So if you're in insurance, you want to have your insurance claims. If you're a car company, you want to have your car company processes, etc. And then on the very right-hand side, it's the pre-training. This is what we've done with the new model. And there's those cool examples, and they're endless what goes wrong. So Chevrolet, they built a model. You could chat with that model. And people said, okay, now recommend me what is it, a SUV car? And the Chevrolet model recommended a Ford car, which is the biggest competitor for them. So this is what you not want to do. And this sounds like super abstract for me, but we had this basically the same story. A German bank, they deployed an LLM chatbot. You could ask it about, hey, what do I need to do to renew my credit card? How can I get a loan for my house? And it worked pretty good. And then people started to blog about it. And then people started to ask that financial chatbot from the bank and said, hey, how can I version an S3 bucket? And how can I change the oil of my car? And it would just reply to all of this. And that was another big fail. And the right one, I've never seen that in person. The Air Canada chatbot, it made up some refund policy. And now the company is forced to pay back people who said, look, yeah, okay, I'll take my money back, just give me the money. That's not good, and a lot of things can go wrong. Now, this is very quick. I just want to give you a quick overview. So we do model serving, serverless. So we serve custom models. We serve a certain number of foundation models and kind of external models where we can limit the throughput, we can control the costs, etc. All this is under one API. We have a built-in vector database. If you see in the Delta table in this catalog, the cool thing is you don't need to set up anything. You right-click on the table name, like here, and then you say, I want to create a vector search index for this. And you give it a primary key, you give it a name. And then, don't quote me on this, but from the fields from the options that we give you, I bet there is a DLT pipeline running underneath because this vector table is also updated incrementally. So if you stream data to the original table, the vector database and table is updated automatically. And then we do fine-tuning, and with all the mosaic, we do also model training. Now, I want to show you a few more things. Yeah, that's cool. 3 minutes, that's good enough. Not here, but here. Okay, first one is kind of intelligent search. Remember the demo that I didn't really show you? If I wanted to know, like, give me information about, it was this motion thing, earthquakes, and magnitude of the earthquake. It would say, okay, I have some tables, do you want to look at them? Now you say, okay, that was basically search, but it's not returning me tables for GIF and for information and earthquake. It just really knows what I want to do, and then it says, here's a sensor table, and if we click on this, in this sensor table, there is actually a column with magnitude. So it's kind of clever. It knows like what I'm searching for. And then the next thing is, well, I have this table, which is a bit bland. I mean, I'm a techie. I would say, come on, this is good enough. But every project manager would say, Frank, please, come on, document this. So I can click here. I say, well, generate documentation. And it generates, I think, pretty good documentation for this column names. Now you say, okay, but this is not perfect. It doesn't have to be perfect. It has to be a good starting point. And then you can still go and accept it, or you can go and edit this. And we also do this for the whole table. So that's one thing. So intelligent search is one. The other one is automated documentation. And then once we have a notebook, let me see if I have one open. Not the one that I was looking for. But once we have a notebook with code, we can also go to the notebook with code and run the assistant, which is showing up here as this tiny wizard. And then remember how I explained you the streaming table, and I told you, well, that streaming table, it ingests exactly once, And a bit confused, usually it pops up on the left, but it just keeps my brain busy. And now I say, like, explain that code. Let's see what it says. And it says, look, this code that you provided, it's using DLT, it's ingesting from Kinesis. It gives you a lot of details. I think this is pretty good. So it's actually explaining all the code. And okay. So we have this assistant. It helps you to find bugs. It helps you to translate code, like from pandas to Spark or the way back. Yeah, so that's the cool thing for data engineers. And then, how much more time do I have? 2 more minutes? For sure, okay. I show you the cool part. The cool part is actually the new model that we have, and it's called DBRX. Now, I'll make it very short. 2 more minutes. I spent 1 minute explaining you. It's a mixture of expert model. That means we have 16 experts. We only use 4, 132 billion parameters. But because we only use 4 of them, of the 16, it's 1/4 of the time you need to get stuff back. So it's incredibly fast. It does 150 tokens per second. We have a base model that you can use to fine tune. We have an instruct model that already understands your instructions. And it's open source. You can use it for commercial applications. It's better by various benchmarks in language, programming, and math compared to the other open source models that you could use. And then obviously the question is always, how does it compare to GPT? Now, if you go to GPT 3.5, you pay $1 per 1 million tokens. If you go to GPT 3.5 is $1 for 1 million tokens. GPT 4, do you know? $60 for 1 million tokens. We are better than GPT 3.5. We're not as good as GPT 4. That was not the goal. So we spent 10 million and 3 months to train it. It was the Mosaic ML group. It brought us on the top list of Hugging Face. If you look at this wild bench leaderboard, above is like Claude and GPT-4. So this is like really, really good. And you don't need to tell me that we won't stay there forever. But now we have the own model, and now we can use our assistant and make it talk to the own model. Things will get faster, things will get cheaper. You have it on Hugging Face spaces. You have it on our playground. You can play with it. The super cool thing, and that's the last thing I'm going to show you live, is we have this playground. And in the playground, you can say, I want to play with this DBRX model, but I also want to compare it to another model. Just pick anyone, like anyone, the Llama 70B. And then I say, do you want some programming or some fun? I say, I don't know, give me code for Spark streaming to ingest from Kafka or Kinesis. Okay, now typically you can see the difference in speed. Depends, sometimes you see it depends on the length of the answer, but it's also measuring it. Sorry, I think I typed the system prompt, did I? I don't know. Give me code for Spark streaming to ingest from Kafka. Not sure what happened. Weird. I don't know. Anyway. Okay, I don't know what's going wrong. I try one more thing. It's actually even cooler. One more thing is the serving endpoints that we have, or the models that we host. Now this one, serving endpoints. So we host our internal model, and we also host the other models like Llama 70B. And now you can, and this ties it back to the Lakehouse story, you can click on query. It gives you the curl and the Python and the SQL. And now you can grab the SQL, like Databricks DBRX instruct, and you can go here to the Lakehouse, and you can open a SQL editor like this one, and then I get here, and then I can say, look, Databricks DBRX instruct, that's our model, and then let me try the same thing if it's working from here. Spark streaming code to ingest from Kafka. And the cool thing is I can run this as a SQL statement. Let me run it. It's running against the serverless data warehouse backend. And I hope it's not affected by the same problem that I had. Ah, no, look at this. Cool. And then it says, sure, here's the code. And it gives you, look, that's the topic. And then it does beautifully the Spark.readStream format Kafka. So that's pretty good, isn't it? And the other cool thing, and that's really, really, really the last thing, we have a lot of built-in AI functions now. And you can use them from SQL, from any SQL, and you can do stuff like AI translate. You can say, do you still like the tourists here in Greece when they ask you where is the way to the beach? And let's see if we can run this. Shift return. Anyone tell me if that's okay or not? I don't know. Sorry, the zoom in was not good. Is that valid or legit Greek? Woo! Okay, so that's the end. I'm so sorry I couldn't do the live thing demo with the phones. This is what I was really waiting for half a year. I'll try to do it another time if you invite me again. I hope I could give you some overview of the Lakehouse and why Gen AI is super cool for the Lakehouse, for data engineering. So Gen AI meets the data platforms, but, and that's even the bigger takeaway, if you think about all those people who do the fancy AI stuff, they will not ever have a good model without good data. So it's all the data engineering behind. Thank you, and